Question 13, Part A. In an experiment, the population of insects, P of t, was modelled by the logistic differential equation, dp dt equals p times 2000 minus p in brackets, where t is the time in days after the beginning of the experiment. The diagram shows a direction field for this differential equation, with the point S representing the initial population. Part 1. Explain why the graph of the solution that passes through the point S cannot also pass through the point T. Let's examine the behaviour of the tangent lines as we move from point S to point T on the direction field. Let's start at point S. If we move horizontally along, we can see that the gradient of the tangent lines are identical, and it's positive. So the rate of change of the population with respect to time is increasing, so the population is going up. Now let's see what happens vertically as we move from point S to point T, but just examining the gradient of the tangent lines in the vertical direction, we can see they're becoming less and less positive. In other words, the gradient's decreasing until we reach this point here. When the population is 2000, the gradient of the tangent lines is 0. In other words, the rate of change of the population with respect to time is 0, which means the population is not rising beyond 2000. Which means that we cannot reach point T. The maximum we could reach is 2000 over time. Let's have a look at the explanation. So I've supplied a little bit of extra detail here, but I'll go through it. So by inspection of the direction field, as the population approaches 2000 from point S, the gradient of the tangent lines decrease from a positive value and approaches 0 as the population approaches 2000. Now at population 2000, the gradient of the tangent lines is 0, indicating a population rate of change of 0. In other words, the population cannot rise beyond 2000 and reach point T. Part 2. On the diagram provided on page 1 of the question 13 writing booklet, clearly sketch the graph of the solution that passes through the point S. When sketching the solution through point S, the curve should follow the general direction of nearby tangent lines. Here is my solution. I've started slightly to the left of point S. So going from left to right, we can see that the curve is increasing all the way through until we reach the horizontal asymptote where the population is 2000, at which point the rate of change of population is 0, indicated by the gradient of the tangent lines being 0 there. Examining the behaviour of this curve from left to right, we can see that the curve is increasing at an increasing rate up until around this point here. This represents a point of inflection. So this is where the rate of change of population is at its greatest. From this point onwards, we can see that the curve is increasing but at a decreasing rate until it approaches a rate of change of 0. Part 3. Find the predicted value of the population, P of t, at which the rate of growth of the population is largest. From part 2, we've observed that there's an inflection point around here which represents the maximum rate of change of population with respect to time. So when examining the behaviour of the curve is increasing at an increasing rate until we get to around this point here, and then from this point here, it's increasing at a decreasing rate. So it's estimated that the population is increasing at its greatest rate when the population is 1000. But let's work this out algebraically. So we want to solve the second derivative, d squared p dt squared equals 0. So we're going to find this inflection point. Now we know that dp dt is given as p times 2000 minus p in brackets. Expanding the brackets, we get 2000p minus p squared. And that's our first derivative, which we'll need to differentiate again to get the second derivative. So differentiating dp dt to get d squared p dt squared, we get 2000 minus 2p. So solving d squared p dt squared equals 0, so 2000 minus 2p equals 0, we get p is equal to 1000. But we need to test whether p equals 1000 represents an inflection point by examining the sign of d squared p dt squared around p equals 1000. Now when p is equal to 500, using this equation here, we get d squared p dt squared's 1000, so that's positive. When p is equal to 1000, we get second derivative is 0, and when p is equal to 1,500, we get second derivative of negative 1,000. So positive, 0, negative. We have a sign change in the second derivative, and that's around p equals 1,000. Hence, p equals 1,000 is an inflection point where the population rate of change is greatest. And this was observed on the direction field. Therefore, the population rate of growth is maximum when p of t is equal to 1,000.